All right, welcome everyone. Actually, we're going to have a moment of, let's see. Moment of making sure, yeah, it looks like we have sound and we can start broadcasting. If looks good. Do you see any option there for asking questions?
No. Usually it comes up.
Yeah. Their latency latency working. Has gotten much better. It used to be like a 30 seconds to a minute behind, and it's now just like a second or so.
To a chat box that I can see. You may not be able to see it because you're going full screen.
All right. Well, would you watch and just let me know if anyone asks a question? All right. Welcome back, everyone. After 2 weeks, I'm glad you remembered where the room was and everything. How is it going with all of the rest of your classes so far? So far, so good. Good. Very busy.
Yeah.
Yeah, and I guess you're going to get busier soon in this class too, where we start off easy and then it picks up a bit as the semester goes along. But don't worry, it's not too bad. So I'm going to start today with going to go over a bit of a review of session 1 fairly quick, but just since it's been 2 weeks since we did it, make sure that to hit the main points again. And we went over these a bit before, but go over in a bit more detail some of these bread and butter descriptive plots that we use, the frequency tables, bar plots, histograms, box plots especially, that are used all the time for describing data numerically. Going to introduce a few measures of center, the mean, median, mode. Actually, I think I'll mention, also the spread, the interquartile range and standard deviation variance, and give you some graphical examples of those as well. And even if you've heard of them, maybe give you a little bit better intuition for what exactly it is they are. Let's start with a bit of a review. The population and sample have special meaning in statistics. And the population being the entire group of interest that includes all individuals or all records or observations or all possible records that could be observed as part of a study. And then a sample is a subset of that population that we want to make using a systematic method, and where every individual in the population has a known and non-zero probability of appearing in that sample. So it doesn't have to be an equal probability, but the probabilities have to be known, and it has to be non-zero for everyone in the population. We're doing a lot of descriptive statistics these first couple of lessons, both numeric summaries and visualization. This is a real part of statistics and how you should start looking at any data set that you start analyzing before doing any inference. And then finally, inferential statistics, which is what much of this course will be about, starting after in the next couple of sessions, where we take our limited information from a sample and make inference about the entire population. So the variable is something we measure. It's something that some attribute or property that is recorded for each of the individuals in the study. And we covered these main types of variables: the nominal variable, which included both binary 2-level and category that were categorical, that are 3 or more levels. Ordinal variables, which are actually numeric, but they're it is the rank that is important. So they're still not really numbers. They're like nominal variables, except that they have an order to them. And then we talked about discrete and continuous variables, which I put together here as quantitative variables, because they often, that distinction between discrete and continuous is not very important unless the numbers are very small, like 1, 2, 3, 4, 5. But what they have in common is that rules of mathematics apply. You can add them, you can subtract them, etc. They're actual real numbers. So for the nominal and the ordinal data, we use frequency tables and bar plots. The frequency table is just a table that lists the number of each of the categories that we have. For a single variable, it's a one-row frequency table. You can make it for 2 variables. Those are called contingency tables. And the bar plot is just a graphical presentation of the same thing. The pie charts, statisticians don't like, except this one. This is my favorite pie chart I've ever seen. And it gets right to the point. It's probably the most direct way of presenting the data of how much pie I have eaten. But even there, I can't really tell what proportion of the pie this is that I've eaten. I know that I've made a good dent in it, and that I probably can't share it 4 ways anymore. But I can't really tell if that is, I don't know, 6 or 40% or 30%, something like that. I don't know, guesses. 30%. 30%? Okay, maybe. I don't know. I guess here it was 35%, and so this is a more quantitative but more boring presentation of the same data. So sometimes the pie chart has a use. So just as an example, we have 40 students, 4 received an A. We can represent this as a frequency, which is the counts. That's what goes in those frequency tables. Proportions or relative frequency, that's a number between 0 and 1, and percentage is that multiplied by 100, so it's between 0 and 100. And you can use any of those in your bar plots or in your frequency tables. In fact, it's pretty common to show both frequency and proportion or percentage in tables summarizing your nominal data. For quantitative variables, there are these 3 different, I mean, there are more than these, but these are some of the main ones. Ordered here in order of from the most detail at the top to the most summarization at the bottom. So the dot plot actually shows every individual data point, and it often puts a little bit of jitter in it to just keep them from overlapping on each other, but it's just a plot of all the individual data points. The histogram does some categorization first, converts your quantitative data into an ordinal variable so that you can order them on your histogram and put bars. So it's like a bar plot for categorical data. And the box plot is a combination of qualitative and quantitative measures put in the form of this box and with whiskers. And the things that we look for in all of these are generally the central tendency where the middle of the plot is, the shape of it, including spread and skew, and the presence of outliers. So this is a dot plot. In this one, some binning has still been done to stack them on top of each other. So it's not exactly putting the original data, but you still see every individual data point. So it's like a histogram, just very detailed. The familiar histogram. Note that so here this weight data has been binned into about, let's see, these are about 12. There's 3 per 50, so there's about 20 or 17 pounds per bin, and so you've created all of these 17-pound bins and then counted the number of people in each one of those bins, so giving the frequency on the y-axis here. But that same data set can look very different depending on the width of the bins that you create. So very fine bins with just a few pounds in each one looks different than with coarse bins. So this is it's important to remember it's a summary of the data, and as necessary for any summary, there's some subjectiveness involved in it, and you could miss things or highlight things depending on how you choose to bin the data. There are always defaults in software, and they're usually pretty good defaults, but there are cases where you can miss certain structure in the data using the default bins. When we're looking at histograms, again, we're looking at these essential aspects of the continuous data, including the center of it, where sort of most of the data lies, where the histogram is higher, the spread, sort of how much it is spread around that center, whether, how many pounds variation around the middle there is, and the shape of it. Is it symmetric, or does it skew one way or the other? Symmetric distribution, of course, is one where if you put a mirror in the center, it looks essentially the same on both sides. And the left skew is one where you see a lot of additional data over towards the left, a much longer tail, and right skew to the right. Some examples of that are lifespan. So if you look at how long individuals in most populations live, you'll see a few individuals who die at a very young age, but not that many. And then you see a lot of people who die at about the same age here in the middle, and then people don't live very much longer than that. So that's a left skewed distribution. And a very good example of a right skewed distribution is incomes, where you have, you can only go down to 0, so there's not too much of a left tail on there. And then you have a lot of people sort of at the lower end of the income distribution, and then a very long tail as you get up to university presidents and CEOs and things like that. Those were what I call single mode or unimodal distributions. There's just one main center of the data, and everything is spread around that. But that's not always the case. You can have a bimodal distribution or even a trimodal distribution. And in the this is usually some kind of indication either of it's not really a single population you're looking at, or there's some important factor, like a binary factor, that is influencing this outcome. For example, if we were looking at weights, if we had collected our data from an elementary school and from, I don't know, a heavyweight boxing school, you have a bimodal distribution because there's that heterogeneity in the population. And an outlier, there's no precise definition or precise and agreed upon definition of an outlier. There are plenty of definitions of outliers, but not that everyone agree on. But in general, it's just some data point that falls far away from the rest of the data points. There's one the definition used in box plots is that it's more than 1.5 times the interquartile range outside of the box. Sometimes there are outliers defined based on the z-score, which we'll get to, of individual points. But all of those are just ways of quantifying something that is really a qualitative observation that this data point doesn't really look like it fits with the rest. And this distance between the next one, what is an outlier on a symmetric distribution like this, might not really be an outlier if this were a skewed distribution. If it's right skewed, you'll expect more points over on that right-hand side. Yes?
Can you make arguments as to whether something's skewed or whether there's an outlier? Like, is there a definition that's used particularly to say something's an outlier as opposed to skewed?
Are there definitions? Not really. I mean, there are tests of distributions. There are statistical inference tests to say, to say whether something appears to, under a null hypothesis, come from a normal distribution, that you can devise tests of symmetry by the fraction of points to the right and to the left of the mean. There are non-inferential tests of skew, such as the difference between the mean and the median. But really, it's an observation. Like
So one paper could say distribution skew, while another could say there's an outlier, or would they define that in the paper?
Most of the time, they would show a histogram and say there appears to be right skew. So there are measures of skew that you can report. There's a skewness statistic that you can report. It's generally not recommended that you report p-values for those kinds of tests, just because from the same distribution, the more data points you have, the smaller a p-value you will get for the same amount of skewness. And generally, for a large data set, you can any small deviation from the distribution in your null hypothesis will give you a small p-value. So what I would recommend is showing the histogram, and then there are statistics called skewness and kurtosis, which has to do with the thickness of the tails, which you can report if it is important to your results to actually quantify the skewness. Usually, what you're looking for is it normal or not? Good question. And as a note, it may or may not be justifiable to remove outliers. Outliers can be there because there was a problem in your data collection, because someone wrote a 1 and it looked like a 7 or something like that. Or it can actually be, it can be a part of your distribution, and just something that is a part of your data and that you can't just throw away. It's a sign that your null hypothesis is incorrect, or there is something that you don't know about your population. Just a reminder, of this box plot. It shows a lot of information on a single plot. So showing the density line here, which is the probability of a continuous value taking values between any range of the continuous variable, with the box plot of it overlaid above. So you have this thick middle line at the median, the value where half are above and half are below. Then the box extends out to the first quartile and the third quartile, so that difference between them is the interquartile range. And then these whiskers, they extend either out to your furthest data point or to 1.5 times the median plus 1.5 times the interquartile range, depending on whichever is smaller. So in this case, there is an outlier, so we know this is going out to all the way to 1.5 times. On this side, there are none, so this might not actually extend all the way out. It won't go beyond the furthest data point. Make sense? The very nice thing about box plots is that they make it easy to compare two distributions side by side. So this example here, the heights of males and females allows you to see that on average, or kind of in the central tendency, males are taller than females. There's a certain amount of overlap between those two distributions. And by the way, there are additions to the box plot in some software that will allow you to do things like change the width of the boxes to show how many observations are in each of them, and also to put little notches on these boxes, such that if they don't overlap, then it's probably a statistically significant difference at the 0.05 level. Yeah.
So those the solid line running horizontally through the interquartile range, those represent 1.5 times the interquartile range.
Yeah. So this width is the interquartile range, and these so-called whiskers are going to the median out to 1.5 times the interquartile range.
Okay, so it's a little bit of an optical illusion because it looks like, to me, it looks like the lines on the right are longer. Maybe that's just me.
Let's see.
And then that lower one looks like the interquartile range, like those two quartiles.
It does look kind of that way. That is, so full disclosure, I didn't make this plot, so it could have been a software that did something different, but that is the standard. Yeah, Tony?
The other thing is, if there's no outlier, then it's the range. Doesn't.
Yeah, but there are outliers here on the
Yeah, one side.
females.
Yeah, if it is on the
So,
other side, that one on the top.
It really should be equal. It should be equal on both sides. There's no reason for it not to be. So,
Unless that's dropping down to the range for the remaining values.
the range for the
In other words,
remaining
the
values.
minimum value for the remaining values that are non-outliers.
Huh, that would be strange.
Well, I mean,
Yeah.
because why bother to go 1.5 out if now the new distribution is different? Right, in other words, if
Yeah.
you drop the outliers.
You actually take the outliers out of the distribution to calculate this?
Well, no, you use the distribution to calculate which are outliers.
Uh-huh.
And once the outliers are out there, then that becomes the rate, the minimum.
Yeah.
That's remaining.
You could.
That's
Yeah.
apparently how SPSS does it.
Oh, that's how
Yeah,
SPSS
that's
does
the way
it.
it looks, because that this
Okay.
comes up all the time on SPSS.
Okay,
That it
okay.
really doesn't look like it's 1.5 times the.
Yeah. Okay.
But I believe that that's what's happening is, once it decides that those are outliers, then those
It
feathers
gets-
become.
it gets dropped.
Yeah, they become the minimum and the maximum.
Gets dropped. Pretty sure that doesn't happen in R, which is why.
That's why you use them.
Yes, you had a question?
Oh,
Chris?
No, I was saying, like, in the book, I thought they said that, like, the whiskers only go out to the data point. And
Yeah.
so if there's like a data point that's like 1 times the IQR, and the whisker only goes to that,
Yeah.
it won't go all the way to the 1.5.
So, I mean, that is what I expect in a case like this, where there are no data points outside. But saying even when there are,
So like, I think the outliers in the females are more than 1.5 times
Yeah.
the IQR, so the whiskers aren't gonna go all the way over there.
so it won't go somewhere in between,
Yeah.
right here.
It's not gonna go out to the point that's gonna represent the value that's in the data set, right?
Yeah, so it's only going to a point that represents a value in the
Oh, yeah.
data set. Yeah, okay.
I could try a couple of them. See if
Makes
that's-
sense.
if that's
One of-
what
one of-
it is.
One of the things I do sometimes is actually overlay all of the data points on top of here, which then makes it easy to see something like that and see if that's the behavior. I'm not aware of ever seeing that behavior in the ones I've made, which are only in R. But maybe during lab today, I'll make a box plot, the same one we're doing in SPSS. I'll make it in R and see if we see this same behavior. But I think that is a likely explanation that it's ending only on a data point. So if you have a data point between that 1.5 IQR or less than the 1.5 IQR, it'll go out to there, even if it would otherwise go right out to here. Thanks. Okay, on to numerical summaries. Here I'm talking about the central tendency measures, mean, median, mode, the measures of various different points in the distribution as quartiles, quantiles, and percentiles, the range, extreme values and standard deviation, as well as some other measures of spread. The mean, which I suspect you're all familiar with, just the sum of all of the values divided by n. This is using the capital sigma notation to represent the sum. Mean is a very convenient measure to use, and we use it all the time. But it is best in distributions where you don't have outliers and don't have strong skew, because it is not resistant. It's affected a lot by outlying values. And I'm plotting here four different distributions. So we have a normal distribution on the left, and what I'm plotting is I'm overlaying on top of the box plot the regular 3 points plus this red bar, which shows the mean. So the black one is the median, and the red one is the mean. And looking here, it kind of, I'm just looking, it does look like the it's a little hard to tell if the whiskers go exactly out to a data point every time. It could be. But here I've overlaid all of the individual data points with a bit of jitter, like I mentioned. And here you're seeing them twice because the big circles here are part of the box plot. These are the outliers, and then I replotted all of the data points using the small black dots, and they're just moved side to side a bit by this jitter that I've added. I've put some R code with the lesson at the end, in case you want to be able to make this. But you see here the normal distribution. This is a symmetric distribution, and the mean and the median overlay on top of each other pretty well, perfectly. The log normal distribution is one where if you take the logarithm of it, you get a normal distribution. And it is a strongly skewed distribution, because it's like a normal distribution where you've then exponentiated everything. So we have lots of what appear outliers on a box plot, and a very big difference between the median and the mean. The exponential distribution, just exponentially distributed, so it would be the exponent of a uniform distribution. Less skewed, but still skewed, and you see this smaller difference between the median and the mean. And finally, uniform distribution. This is generated just so that the values are equally likely to be anywhere between -2 and 2 here. And it's symmetric, so there's not very much difference between the median and the mean. Are there any new distributions here to anyone? Is anyone unfamiliar with the log normal or the exponential distribution?
I just wanted to ask quickly about resistant, same as robust, correct?
Same thing as robust. Yeah, it's not robust to outliers, but not resistant. Yeah, I mean the same thing. All right. So the median is just the midpoint of the observations. If you have an odd number of observations, it's just the middle one when you rank order them. If there is an even, and this is one definition, the average of the two middle observations. It turns out that actually there are a bunch of different ways for calculating the median in this case. And if you use the function in R, it gives you, I think, 7 different options for how to calculate the median if you look in the help page. And there's one of them that will give you the same answer as SPSS. These differences you only really notice with a small number of points. If you have 4 data points, there can be a pretty large difference in the median depending on how you calculate it. If you have 100 data points, you won't notice the difference. But it's also the 50th percentile. Just a few examples here. 1, 2, 3, 4, 5. The median is 3. We replace the 5 with a billion. It's the same. So that's what I mean. It's it's resistant. It's robust to outliers. And if we get rid of that 5, it changes a little bit. It has to be somewhere between 2 and 3. My other favorite example for today, the 7 dwarves. The median is just right there. If we have them rank ordered in terms of height, it's the middle one. And if we replace one of them with a basketball player, it doesn't change the median at all. So the mode is the most common value, and it really only makes sense for categorical, ordinal, maybe binary data, really for categorical or ordinal data. And when we talk about the mode in a continuous distribution, it is entirely dependent on how the data are binned. So in this example, our mode is right here, whatever the second bar is. But if we were to change the width of these bars, you could end up with a different mode. So getting back to your question about a numeric or some kind of a quantitative summary of skew, this is one way to do it. That in skewed distributions, it brings apart these 3 measures of central tendency, the mode, the median, and the mean. And a fairly common measure of skewness is the difference between the median and the mean. So if you have a mean that's larger than the median, it means you're right skewed. Your mean is less than the median, you're left skewed. And the more skewed it is, the bigger that difference is.
Is there a number that they tend to use as far as that difference goes? I guess it would be proportional depending on the time set is.
Well, we'll have units, so it'll be in the same units as whatever you're measuring. But I don't think there's a number that above which you say it's a skewed distribution. That's better for comparative purposes, I think. If you're, if you have a bunch of different distributions or something, you could order them by skew just using that difference. But that's not a statistic that I would probably report in a paper. That would just be exploratory. So the peak percentiles are the percentage of the data that fall below P. So the 90th percentile would be the value below which 90% of the data fall, which could be another measure of skewness if you were to look at the differences between each of these percentiles. You would see increasing differences between the percentiles as you got further to the right on a right skewed distribution. Quartiles are just special percentiles. They're the ones that split the data into 4 equal parts, the 25th, 50th, and 75th percentile. So the median is that second quartile, the 50th percentile, and the first and third quartiles are the ones below which 25% and 75% of the data fall. So here's an example of a distribution split into 3 quartiles. This being a skewed distribution, you see how this there's more range of values to the right of Q3 than there are to the left of Q1. Range, one more measure of spread, and it's just the difference between your most extreme values. It's the difference between your largest value and your smallest value. So it's a useful thing just for describing the total amount of variation in your data set. But of course, it is strongly affected by outliers, and it's also strongly affected just by sampling. Whereas something like the average is fairly stable under repeated sampling, and becomes more and more stable as you get to larger sample size. The range is unstable, as are the max and min. The more data you collect, the more it will keep changing. So it does not necessarily get more stable as you get to larger sample sizes. So here the range would be difference between 25 and 100, so 150. Variance and standard deviation, we calculate these by you first need the mean, you calculate the difference between each individual data point and the mean. You square those, and then you divide by, depending on whether this is a population or a sample, you divide by n or n minus 1. This s squared says this is from a sample, so I'm dividing by n minus 1. The reason for this is that just as a hand-waving explanation, in a sample we are calculating this x bar from the sample. And so because you calculate that in the place that minimizes these deviations, you will tend to get too small of a value for this. And if you divide by n, you will underestimate your variance. And it turns out if you divide by n minus 1, this is the number of degrees of freedom in this statistic, you get an unbiased estimate of the population variance. If this x bar, what would we call this if this were something known from the population? What would I use instead of x bar? Mean? Yeah, how would I represent it? You remember this?
Greek letter.
Greek letter, yeah. Yeah.
I remember it well.
Mu, yeah. Yeah, so if we had mu and we used this here, then this would be divided by n. Even if these x's are from the sample, if we have the population mean, then we don't need to make this correction. This correction is here because the mean is estimated from this sample. What about a weird case? And I've never actually thought about this before, so think this through with me. What if for some weird reason we had one sample that we used to estimate x bar and another sample that we used where we used these xi? Would you want to divide by n or by n minus 1?
Are you measuring the the variance within the sample compared to another sample?
Well, I'm using the mean that I got from another sample to calculate the variance of this sample. Yeah.
So why would I use n minus 1 instead of n?
Or what would you use? Would you use n minus 1?
I would use n minus 1.
You'd use n minus 1?
Yeah.
How come?
I mean, if you're measuring the variance, eventually you're going to have to measure one value against itself, right?
Uh-huh.
So that would end up being 0.
I don't know. What do you think?
I think you will use n minus 1 because the mean that you're using is only estimate from another sample.
Because you say you'd use n minus, so you both would use n minus 1 for different reasons. Well, here's my thinking. This correction is here because when you estimate, you choose the value of x bar that minimizes the variance. So you're not using the actual population mean, you're using a mean estimated from the sample to minimize the variance. So you underestimate the variance. You can imagine that the mean that you estimate will be pretty close to the population mean, but it'll be moved a bit from one way or the other in a way that actually reduces your estimate of the variance. And so you have to you have to make this n-1 correction so that you're not underestimating the mean. But if you got the mean from another sample, you're not going to be underestimating the variance anymore, because that mean is not in the place that minimizes the sum of squares here. And in fact, you're gonna, well, you tell me, if we just use n, are you gonna underestimate, overestimate, or properly estimate the variance in this second sample? So we have a somewhat inaccurate mean from sample A that we plug in to calculate the variance in sample B. You're going to underestimate or overestimate the mean, or sorry, the variance.
We were saying we're going to get it right, right?
If
If we use
if you use the population mean, you get it right, and you put an n on the denominator.
Right.
But this isn't the population mean; it's the mean from some other sample. So it'll have some error in it.
I guess you would want to use n, so you would rather, because you don't want to underestimate the mean.
Yeah. How about this? Give me a thumbs up if you think we're going to overestimate the variance, and a thumbs down if you think we're going to underestimate it, and like this if you think we'll be right on.
Using which?
Using the mean from an independent sample and dividing by n. Underestimate, under. Seems it's about a coin flip. Okay, well, listen to me through here. If we have the population mean mu and we divide by n here, we get an unbiased estimate of the variance from this sample. But if this were from another sample, we know that there is sampling variation in it. So this is going to be a bit different from the population mean. And if it's a bit different from the population mean, it's going to increase these deviances, right? So we're going to get an overestimate then of the variance, because there is error in the mean from another sample. And I don't know how you'd correct for that. You would have to use something else here, and it would depend on the number of observations that were in your other sample. Because if you had a very large sample that this mean was estimated from, it would be approximately divided by n. And if it was a small sample, there would be a lot of error. You'd have more of an overestimate, and you'd have to have a correction on here on the left that depended on that other sample size. That's just an aside, but just to get you thinking about, start you thinking about sampling and about differences between populations and samples. Yeah.
So we're assuming that the problem, that the difference between the sample and the population variance is because of in a sample is because of the sample mean not totally reflecting precisely where the population mean is, right?
So your comment is that or you're reflecting back that when you estimate the mean from a sample, it doesn't totally reflect the population mean.
I'm just clarifying if that is
Yeah.
the case. Okay, because I'm just wondering, because the error might come from like the other side. You don't have enough, your data points. You don't have as wide a range of data points as the real population, right? Isn't that like an equally plausible possibility for
So you're
error and variance?
right. So you're making the point that your amount of uncertainty in this variance estimate will depend on what n is. The higher n is, the less uncertainty there will be in this estimate. If n is only 2 or 3, then there will be a lot of uncertainty in this estimate.
I guess effectively,
Yeah, and that's true. And we're not getting it. We're not addressing that at all here. That is sampling variation. That in small samples you have more differences from one sample to another. Whereas if you have a large sample, you have n equals 1,000, you're going to get pretty close to the same answer if you do the same thing twice.
but you always need n minus 1, regardless of how
Right,
powerful, how
right.
big the sample is.
The point is, so that would be random sampling variation. It would be symmetrically distributed around the correct population value. But if you don't make this correction here, then you'll be systematically off. You'll be biased towards underestimating the variance if you just go 1 over n. So there's bias and then there's variability. This n minus 1 takes care of the bias, but you're still going to have sampling variability.
Would the increase or decrease in the variability between the first and second sample set, depending on which mean you use, depend on whether the mean was higher or lower than the one you're comparing it to originally?
Sorry, could you ask that again?
So let's say the mean of your first sample is 51. The mean of your second sample could be either 53
Yep.
or 47.
Yep.
Wouldn't the difference in variance or the direction of difference depend on whether that was higher or lower?
The direction of difference depends on whether it was higher or lower. I don't think so, because any deviation, remember that when we calculate x bar from this sample, it is the x bar that absolutely minimizes the variance. There is no other value of x bar which will give you a smaller variance.
Okay.
So in either direction, any other x bar, any other estimate of x bar will increase your measured variance here. Yes.
I feel that my understanding is that because you are taking a square of the differences, and that's why it doesn't matter if the mean turns out to be a large number or small.
That is right. It's because you're squaring the differences. Variance is always positive, and because the mean of your sample is the value that minimizes this. So, yes, that is an important piece of the equation, that it is the square. If it were not the square, then you could always get a smaller value of the variance. So if we got rid of this, then as you just keep on making x bar more negative, variance always keeps on decreasing. So good discussion. Thank you. I've never actually discussed variance so much. Usually kind of take it for granted. And by the way, when you click standard deviation or variance, or you do your descriptives in SPSS, what do you think it uses? Do you think it uses n minus 1 or n on the denominator here?
What's the question?
The question is, do you think statistical software would assume that your data are from a sample or from a population? Sample. Yeah, you're right. Okay. Just to kind of highlight emphasize these deviations and the square deviations, I actually plotted some of them. So from each of these 4 distributions, I have plotted the population mean. So this is no, sorry, I actually calculated the mean from these samples here, and then calculated the differences between each data point and that sample mean, and put that in red. So you can see that it depends on where your mean is and how far each of those data points is from the mean. And it's positive or negative, except for the for the log normal. Oh, I just plotted each of these from 0 in these two cases, not from the mean. So these are deviances, and here are the squared deviations. So whereas here on the normal, the largest deviation is about 2. Now it's up to over 5, and you just see how a lot of them are really small. And especially in this really skewed log normal distribution, most of the data points just look like right down around 0, with a couple of them really, really dominating these squared deviations. So, this one data point here is contributing almost as much to the total deviations in the log normal distribution as everything else combined. Whereas in the uniform, where there are, the tails are perfectly flat, there isn't even, it's a very compact distribution. You see that they're pretty well evenly distributed between 0 and 3. Just a few notes about standard deviation. It has the same units as your observed variable. So if your measurements are in pounds, your standard deviation is also in pounds. It's a measure of the spread of the data such that if it's 0, that only occurs if every one of your observations is the same. And as soon as there is any variability in your observations, 2 values that are not the same, then it has to be greater than 0. And the more spread there is around that mean, of course, the larger the standard deviation gets. It is not resistant or robust to outliers or skew. So why do we use it? Why did I start out by telling you about standard deviation if it's not robust to these things? Yeah.
Well, you just said it in the prior slide that it is convenient for describing normal distributions.
Exactly. Paying attention. Thank you. Yes, it is convenient for describing normal distributions because it's one of the 2 parameters that define a normal distribution, the mean and the standard deviation. We work with normal distributions a lot, even when we don't have perfectly normally distributed data because of something that we will get to called the central limit theorem. So it's a very important distribution for analyzing all kinds of data. On this one, I have added a little bit more decoration to that box plot. So before we had the mean and the median, and then I've just added to this the mean plus or minus 1 standard deviation as the narrower red line, and plus or minus 2 standard deviations to the plot. So on the normal distribution, you see them, the 1 standard deviation is kind of like where the boxes are, the interquartile range, and 2 standard deviation is kind of about out to where the whiskers go. But in this log normal distribution, all bets are off. They're very different in the 2 directions. Can't even see the mean minus 2 standard deviations here. And just like the mean, they're influenced strongly by outliers, but even influenced more than the mean is. So here you see the mean only goes up about that much, but the two standard deviations is really affected a lot more than the mean by the skewness of this distribution. There are some alternative, more robust measures of spread, the interquartile range that I've mentioned, which is just the difference between those 2, the width of the box in that box plot, the third minus the first quartile. The median absolute deviation, or the MAD, is actually a reasonably commonly, well, IQR is, I would say, the most commonly used alternative measure of spread, maybe followed by the MAD, which is similar to the standard deviation for a normal distribution. It's just instead of wait, this should be squared here, sorry. So it would be each individual observation minus the median. Sorry, this should be the absolute value here. So this needs to be the median of the absolute values of x minus the median of x, so that they're always positive. I wonder if I can write that on here. No, I can't.
So wait, I'm sorry, it's the median multiplied by that difference?
No, so you calculate the median of all your data points, and for each individual, you take that observation minus the median, take the absolute value of that, and then the median of all of those absolute values. So you need your median, you need the absolute value of the differences from that median, and then you need another median. Questions?
Where does that second median come from again? Sorry.
The second median?
Yeah.
So it's the median deviation from the median. So your first median is just the median of all your data points. Like if say we're talking about age, it's your median age. And then everyone's individual age, you would subtract that from the median and take the absolute value. So if the median is 30 years old, someone is 25, the absolute value of that difference is 5. If they're 35, it's also 5. So it doesn't matter whether you're above or below it. So for everyone, you calculate that absolute value of how far they are from the median, and then you calculate the median of all of those. So that's a robust alternative to the standard deviation that has about the same amount of spread for a normal distribution.
So that would work even if it was skewed?
Yep, so it would
It would
be,
give
it would, I mean, it would still be a bit affected by skew, because skew does, if we look at here, skew does still affect the median a bit, but it's much, much more resistant to skewness than the standard deviation. And yes, you could still use it for a skewed distribution. Of course, for a skewed distribution, any measure of spread isn't going to tell you the whole story. It's not telling you that there's more spread on the right side than on the left. It's a measure of spread around the median. So it's a measure of spread around this point here. That's not exactly it. It is one center of the distribution, but it's a partial story. If you have a skewed distribution, it would be better to use the MAD than a standard deviation to describe its spread. Finally, of course, the range, this very non-robust measure of the total variability of the data. All right, just so you have it on your slides, a summary of all of the things that we have covered today that you should remember, things that you should be familiar with before your first exam, and that you'll go over in the assignments. I did, by the way, put both these PowerPoint slides and a PDF, a 4-per-page version of them on Blackboard. And as soon as we have an industrial type printer here, I'm going to start printing those notes and bringing them into class. All right, I'm going to wrap up here. Any questions about any of the stuff we've done today or about the class in general before I give you a little bit of a break and we go on to the lab? All right, thank you everyone, and thanks to everyone who attended online. I hope you had a good experience. Any feedback about your online experience for those who are online would be welcome.